Stevance with us in the second talk session of STEMS 2021. She is originally born and raised in France. She studied physics and astronomy at the University of Sheffield and worked as a support astronomer at the Isaac Newton Group in La Palma for a year, obtaining her master's in 2015. She completed a PhD studying the 3D shape of core collapse supernova in 2019. Currently, she is a research fellow at the University of Auckland. So, hello, Sia, how are you?
Hi, thanks so much for having me. I'm really good. How are you?
Yeah, I am also good. So currently, what's time zone you are like? What is the time there currently? It's 9 a.m. in India.
It's about 4:30 p.m. on Friday. So much finished. I'm happy about that.
Okay. So first of all, let's start. So, what is the field which you are currently working on? So, what are the topics on which you are currently working on?
So I work on a couple of things. The main topic of my postdoc is to better understand the origins of kilonovae and gravitational waves, so black hole mergers and neutron star mergers and that kind of stuff. And the way we're trying to do that is so you may have heard that there was a neutron star merger in 2017. Called 170817 sometimes. It's the first one we ever saw, and it's the only one where we also have the light from it. And because we have the light from that kilonova, we managed to pinpoint which galaxy it was from. And so people took beautiful images of the galaxy, and that allows us to study the regions near that explosion to better understand how these stars evolved together to give us the progenitor of the binary system, so the two stars rotating around each other that gave us the gravitational wave. And so our goal is to go back to look at those images again. They've been looked at before, but do it with some state-of-the-art binary stellar population codes. So those are written by my boss. And what that means, binary stellar population, is that you are trying to understand the evolution of stars when they have a companion. So not just when they're on their own, but when some of the stars, not all of the stars, also have a companion. And it's super important to include binary stars because there's loads and loads of binary stars in the massive star population. And when you have, two neutron stars merging with each other, it's a binary. So magic, we have it. So that's the main goal of my postdoc is to do that. But I also have fun with supernovae and other things.
That sounds cool. So you said that you study the images which have been found before and then go back to where did the light came from, and then you study the galaxy from which it came. So how do you exactly do that? Can you tell us something more about it? How do you find the galaxy and all that?
Okay, so the galaxy was found back in 2017. And the data that I said was already studied has been released. The reason we're going back to it is because they studied it with single star populations. So evolution codes that only take into account single stars, and then they just kind of assume it's close enough for the binary stars. But that data comes from actually the Very Large Telescope. So it was, I can't remember what telescope found 170817, but it wasn't a big telescope. It would have been when 170817 happened, it was the worst kept secret in the astronomy field because nobody could talk about it. But a third of all astronomers were trying desperately to find this thing in the night sky, and all the telescopes were requisited. People are told you can't go in the control room. We're going to take the first 2 hours of your night because we have to use the telescope for something we're not going to tell you about. Everyone knew it was about that. So they did that for the VLT, and my partner was actually at the Very Large Telescope at the time.
Okay.
And so they requisited the first 2 hours of the night to point the VLT at it when they knew the position of the explosion, and they took beautiful pictures with loads of different instruments. And the one that we are interested in is called Muse, and it's very special because it doesn't just take pictures. like each pixel in the picture is also a spectrum. So it's magic, basically. It's amazing.
Oh, that's nice. That's nice. So you were talking about some kilonova. So can you explain a bit more about that?
Okay, I can totally do that. So, kilonova is, so compared to gravitational wave events, like with respect to that, the kilonova is the light. So if you have a neutron star merger, you get the gravitational waves as they spin around each other closer and closer and closer and faster and faster and faster. You get the gravitational wave. And then when they merge, they make a big mess, basically. One neutron star gets completely disrupted. Well, not completely, but they don't merge nicely. They explode all over the place. And that material is very hot. It's shocked. It creates loads and loads of new elements. And these new elements are super radioactive because they've basically been fired with a whole bunch of neutrons and they're not stable. And because they're not stable, these nuclei, they have to decay back into a nucleus that is stable. And that radioactive decay, the product of it is, well, one of the products is photons, so light. And so you get this tremendous light from this kilonova. Now, the reason it's called a kilonova, and it's not like a supernova. Well, it has similarities in the sense that the light is powered by radioactive decay, like I said. But a supernova is from a different kind of stars. It's from either a massive star that has reached the end of its life and the core collapses and then the whole thing explodes. Or it's from a white dwarf, which is like the dead core of a star like the sun. And if the white dwarfs are get too big, either because they're too close to another companion star or because they have a friend that they end up merging with, then you get a supernova as well. And the reason that they have these names is because of another kind of astronomical explosion called a nova. Now, a nova is kind of, it's like it's the white dwarf supernova, but more tame, where just the outer layer explodes. And the reason they all have this root, nova, is because of Latin. In the early stages of astronomy, in the 1600s, people were finding these new stars, so stella nova, that's new star in Latin, and in Europe, Latin was the language of science. And so nova kind of stuck around as this word for these new stars that you see in the sky. Now, they're not stars. We know that nowadays. They didn't before. And we know that there are loads of different kinds of explosions that can give you these apparently new stars in the sky. So there's these novae. The supernovae are called supernovae because they're much, much, much brighter. And that distinction happened in the 30s, where people were like, oh, this nova is much further away than we thought, so it has to be much brighter. And kilonova has come about because some people did some calculations and realized that they would be about 1,000 times more powerful than a nova, hence kilonova.
Oh, the names are very quietly about. That's cool. So you just mentioned that in 1600s, people were discovering in Europe about supernovas and supernovas at that time. So this question naturally arises that what led to the interest in discovering all these astronomical objects? So, for example, in like early ages, people had to count something or people had to do something with the instruments or something. So they discovered maths, they discovered physics and all that. But what was the reason behind which people got motivated to search for these astronomical objects far into space?
That is such a great question. So I will say, by the way, that novae were not discovered by Westerners in the 1600s. That's just where the term comes from. The first supernovae that we know of seen by human people were found in Chinese records, thousands of years ago. So the Chinese people were on it much before us, but the English term comes from a Western language. And the reason that people looked at it is because of astrology. actually. It's because people looked up at the sky to try and, because they found a lot of meaning in the stars and they were trying to make predictions. So whether it was for religious purposes or because astrology was not considered a religion, it was considered a science back in the day. So that's why people looked at the stars, either because of religious purposes or because of astrology as a science where people made predictions. And what was very interesting is that back then, when the predictions from astrology weren't correct, people didn't think, well, astrology doesn't work. They thought, shit, we got the positions of the stars wrong. We must have gotten the positions of the stars wrong because that didn't match. And so that was the motivation back then. And something like a new star happening was a very strong omen because it's such a rare occurrence.
So I didn't know that astronomy and astrology were so closely related at back then. I was thinking
no, really. And in the 1600s, the difference wasn't very big. Like some of the biggest Western astronomers we hear about, like Tycho Brahe and Kepler, Kepler's laws, they were astrologers.
Oh, okay.
They were astrologers. That was their job. That's why they did what they did. And so science came with it, but the goal was the astrology.
So whatever I was thinking till date, it goes wrong. I was thinking they're like physicists from the profession only. Okay. Now the similarity name makes sense. So okay, that's cool. So okay, can you tell us some simple results about astronomy or some simple discoveries about astronomy, which were simple enough to understand, but they had a quite big impact on the field of your study. So can you tell something like that?
So like a recent discovery?
Yeah, it may be recent or it may be old also.
Oh, that's such a good question. There's loads and loads of
that was simple at that time when it was discovered, but it has a very big
I've got a great one. Did you know that 100 years ago people didn't know that there were other galaxies?
Okay. Okay,
I've got your attention now. I've got your attention now. So here is how people found it. Was about 100 years ago that people figured out there were other galaxies. And the way that that happened is because there were amazing women working at the Henry Draper catalog team in America, and they were classifying loads and loads and loads of stars of stellar spectra, because spectroscopy was becoming like a big science because people could take pictures. Like photography was becoming a big thing. And so people were taking pictures of these spectra and classifying them. And one of the women at the observatory, and Henrietta Leavitt, she realized there was a correlation between a specific kind of star and their period. So Cepheids, that's the word I was looking for. I was trying to talk and at the same time remember the type of star, but the type of star is called the Cepheid variable. So these are variable stars that their brightness just changes over time. Slowly, it goes up and then it goes down, then it goes up and then it goes down. It's because of something that happens in the envelope of the star where it expands and then it shoots back in and then it expands again and then it shoots back in. And she found a very, very good relationship between that period of like how long it takes for it to go up and down, and the absolute magnitude, so the absolute brightness of the star. And the reason that's so important is that because if you know the absolute brightness of a star, you can figure out its distance, because you see how bright it looks to you. If you figure out how bright it's supposed to be, you can infer the distance. So this was a great distance indicator. And soon after that, a few years after that, Hubble, like the Hubble Space Telescope, but the person, had a photographic plate of Andromeda. And he found one of these Cepheids in there, a variable star. And actually you can see the plate and it's got like a big red pen, like variable. And because he found that Cepheid in there, he could actually compute the distance to Andromeda. And at the time, something like Andromeda was like called a nebula because it was fuzzy. It was a bunch of stars, but fuzzy, but they didn't know how far it was. But because he had that Cepheid variable and that relationship, he realized that this thing was much further away than anybody had thought before. And it was actually a galaxy outside of our own, like a whole world away. And so, yeah, 100 years ago, people didn't know that there were other galaxies.
That's quite interesting. So how many, like after that, we have found out so many galaxies. So, but at that time, people had this big misconception that, okay, we are the only...
People knew, so there were loads of, like, I guess galaxies were known, but people didn't know there were other galaxies. So then they had found these like nebulae, like these like cloud-looking things.
Okay.
They just didn't know how far they were, and so they didn't recognize them as being other galaxies. But once one was found, then people could start to deduce that these things were galaxies as well, and they could start looking to try and understand their distance to really evaluate how far they were.
So this arises a question in like, so people generally, when something is not discovered, so people generally have some misconceptions about something. They think, okay, this might be true, but it turns out to be false. So can you tell me something, some misconception which happened in astronomy, but which turned out to be false, and that misconception was like huge impact on that time, but after the discovery was made, it changed everything, something like that?
Oh, that's such a good question. Because you asked me that question, I thought it was like a misconception that the layperson has, not astronomers have. But that's a really good question. It's how to find.
Even a layman's misconception is like, you can also tell us.
Sorry?
Even a layman's misconception, you can also tell us. Even we can also have that misconception.
You're too nice. Well, okay, so I'll give you a physics misconception and then a layman's misconception. So I remember when I was an undergraduate seeing a quote from Kelvin, Lord Kelvin, yes, like the universe.
Yeah.
Who basically said, there's nothing left to discover in the field of physics. All we'll ever do now is find more accurate measurements. They hadn't split the atom yet. So he was very, very freaking wrong. So yeah, don't listen to old men. No, I think one of the most striking layperson misconception I see is people struggle to realize first how big the numbers are in space, but also how empty space is. And I think I blame movies for that, because when people picture when people picture the asteroid belt, they think like there's tons of asteroids everywhere and blah blah blah. Like there isn't, like you could fly through it and see nothing. And space all over the place is just the same. It's very, very, very empty and very, very large. And it's difficult to picture it on a human scale, even for astronomers. That's why we use the scientific notation, so like 10 to the power of something, to express pretty much everything. We use logarithms a lot because the scales are so large, you can't work in linear scales. There is just no way to actually capture this intuition as a person, because we're used to things that are just our size or the size of a building. So yeah, space is massive. Absolutely massive.
Yeah, and also, I also had a very difficult time with visualizing these numbers in physics. Like some said, okay, observable space is 10 to the power 43. Like, okay, how can we get 10 to the power 43 can be? Like,
it's pretty insane. It's ridiculous. For me, the worst thing is the small scale, because I'm used to working on the very large scale. I'm like an extragalactic astronomer, so I work with things that are pretty far away. But my friends who are like tiny things, and I cannot, because I don't work with it. I'm not used to it. And it's mind-boggling to me how small these things are. Or like the early universe, the Big Bang, how small things were, the tiniest amount of time, and how much of a difference it makes. It's like, it's magic.
So, as you raised about Big Bang, so let's talk about something about Big Bang. So we have generally we have heard that Big Bang was some explosion where the universe was created and all that. So and we haven't also found, if I'm not wrong, that what was before Big Bang. So what happened before Big Bang? Maybe we are not very clear of. So
yeah, go on.
Yeah. So can you tell me? So is there something related to before, what happened before Big Bang? So
it's not my field, but from what I understand, the Big Bang is the limit of what we can observe, if that makes sense. So people might be able to understand, to try and come up with a theory of what happened in order for the Big Bang to happen, and etc. But it's actually we can't I don't think we can even yet get to like T0, because physics breaks down at the very, very earliest times of the universe because of the temperatures and the energies and everything. Like the forces are messed up and combined and all of that.
Right.
But because it started with a singularity that we can see, like all the stuff that is in our universe starting from what, form of singularity mathematically, like it's not just like a tiny point that exploded. It's just mathematically that's how it's represented, and it's also the origin of time, and you can't go to time minus 10, like it doesn't work like that. So you can't observe anything beyond that, and actually in terms of actually observing, so when I say observing, I mean like observing the influence of anything beyond that. That's what I mean, observing the influence of that. In terms of actually observing, we can't even go back further than 380,000 years. That's the earliest photons we have, and that's called the cosmic microwave background. And that's when the first photons managed to escape. And that's the first observation we have of the universe. And everything we understand from the earlier universe is kind of derived from that and other things that we can observe today, because we can't probe something that we can't see.
Right. That's okay. That's good answer. So coming back to our recent discovery, so recently NASA discovered that there is water on the surface of Moon.
Yeah.
Yeah. So can you tell us more about that?
Okay, so that's actually quite interesting. So, I mean, all of it is interesting, but what's interesting with this is we already knew there was water on the Moon. We knew there was water ice on the poles. What's special about this is that it's water on the sunlit face of the Moon, so the face of the Moon that faces us. And there were two papers as part of that particular press release. The first one found the water, and that's what most people talk about. So it found water in the exosphere, so it's like the tenuous, tiny atmosphere of the Moon. Okay. It found traces of water, so it knows without question that there is water there. The other paper is about something they call micro cold traps. So they're cold traps. So that's areas of the Moon that are in the shade and that are always 110 Kelvin or less, and micro as in small. So they're between a centimeter or a meter. And the reason that these micro cold traps are important is that they could be prime locations for water ice to hide from the harsh radiation of the sun. And the reason that people are interested in finding water ice on the Moon, so by the way, because that water in the exosphere is not water ice, but it has to come from somewhere. So it could be either water ice or it could be what they call impact glasses. well, that's what it's called, impact glasses. Glass is a form of rock that, so if you have lava and it cools super quickly, it forms a glass like basalt, and it's a rock that if you cut it, it looks very smooth. It has not had time to crystallize or anything. And some of these glasses can contain water, and if you heat it up, it just evaporates. And so you can get these glasses formed on the moon. If you have like a meteorite that impacts the moon, then it melts the surface and then it cools very quickly because you're in space, and then it makes these, and it can keep some of those volatiles that have been brought in, volatile as in from the meteorite. So those impact glasses, the microcold traps, the ice water could be good locations to mine water on the moon. And the reason you might want to do that is, well, there's two main reasons. One is because if you want to form a base on the moon or habitat, you deep water. That being said, we're pretty good at recycling water in general. The International Space Station is pretty much a closed system, so all of the water you drink and everything gets recycled. But another reason you might want to do that is because water can give you rocket fuel. So water is hydrogen and liquid oxygen and liquid hydrogen, and a spark gives you a giant explosion. And if you put it on the end of a rocket, then you can do things. Yeah. And the reason you do that on the moon rather than Earth is because rocket fuel can be heavy. And the hardest thing, the most energy consuming step of space exploration is escaping the gravitational field of the Earth, because the Earth is really heavy. And so if you can make your fuel outside of the main gravitational field of the Earth, then it's a lot easier. It's a lot, well, you're wasting less fuel, because otherwise the more fuel you make, the more fuel you have to make in order to get it off the planet. And it's a mess, it's exponential.
Exactly. Oh, that's a pretty useful application. I didn't think of that. So, can you tell us that how the water was discovered? Like, what was the method to discover water?
So the way they found the water. So first of all, in a previous study, they found. So they looked at spectra in the infrared using SOFIA. It's a telescope that's mounted on a plane. It's really cool. And they found infrared bands, so like lines, in the 3 millimeter band, so 3 millimeter being the wavelength in that case. They'd found out a few years ago, but it could be either water or hydroxyl. So hydroxyl is OH, water is H2O. And in order to figure out whether it was hydroxyl or water, they looked at the 6 millimeter band, because that is a telltale. Actually, the 3 millimeter might not have been SOFIA. The 6 millimeter was definitely a SOFIA observation. But the 6 millimeter band is a smoking gun piece of evidence that tells you it is water. And that's why they looked at it. So it can't be any other element. It has to be water. If that line that they saw is statistically significant, it must be water. And so they used that to also try to calculate how much water was in the atmosphere. And it's about 100 to 400 parts per million.
Oh, that's nice. That was an interesting insight into that. So there's another thing which we would like to discuss with you. So a few weeks back, there was a viral video on Twitter about a girl saying that maths is fake. Why do we do algebra and all that? So what are your views on the same?
On what? Sorry, I didn't hear you very well.
A few weeks back, there was a viral video on Twitter also spreading a girl saying that maths was fake. So what are your views on that?
I think the video wasn't that maths was fake. If we're talking about the same video, it was a girl saying that she did not understand how maths was real. She said, I know that it's real because people make it work, but she was asking how, and how did it come about? How did people come up with maths?
That was the video.
And that was such a good video. It got a lot of hate on the internet. I think it's because she's 16 and like the internet loves to hate young women. It's like, oh well, her questions must be stupid. It's like, actually they're really fucking interesting. It actually sparked a lot of really interesting conversations on the academic Twitter, where some mathematicians were discussing, like, is maths created or is it discovered? And people have differing opinions because, it's kind of a philosophical question. And so this was a really it was really interesting. It's a shame she got so much hate for it, but yeah, everyone has different ideas. Like, so some people argue that even if you took away all of our knowledge of maths, it would be rediscovered because it just explains things that are there in nature. But some people argue that maths is just one way that we try to make sense of the universe, and that you could, come up with an alternative system that's pretty different and would do the same thing. And it's like, you can't prove that. It's kind of a philosophical question, and it's really, really interesting to me.
So yeah. So that was a very good discussion also. So anything more which you would like to tell us about astronomy which we don't know? So generally it is not like known to general audience, but it's a quite interesting topic.
Something you might not know. There is a phase of that's one of my favorite astronomy facts.
Okay.
It's astronomy / physics, and it kind of goes to show that physicists shouldn't be allowed to name things. There is a phase of matter called nuclear pasta.
Okay.
Nuclear pasta, like the food, and it's found inside of neutron stars. And the reason it's called nuclear pasta is because the density is so high inside of those neutron stars, that matter kind of melts together, and so you've got this weird neutron soup. And the neutrons do weird things together. They like make like laminars, so kind of like lasagna. They make like long strand things that are more like spaghetti, and they make ball shapes that are like the meatballs. And so physicists called it nuclear pasta because things inside, you find it inside the nucleus and it looks like pasta, so it's nuclear pasta. It's a real phase of matter that happens at very high densities. Very high pressures, and the only places in the universe that it occurs is inside neutron stars and stuff like that. So, here is your stupid fact of the day.
Yeah, that's interesting, and now it makes sense why physicists shouldn't name the things. So, Heloise, so would you suggest something for our readers to look upon, or some sources or some books which they can look upon?
I don't read books that often. I read papers a lot. So
any source for which they can look upon it.
Let me think. Are movies okay? Like good science fiction. Is good science fiction okay, or do you want just educational resources?
Yeah, also science fiction is good because that increases the curiosity among people.
There's one great Netflix series I watched the other day called Away, which people might have seen already, and it's people going to Mars for the first time. It's the first team, and it's very, very well done, and it explores the dangers of space, but also international relationships, because when you do something that big, many countries work together, and how people react under like high pressure situations, because when you're in space you're on your own, especially when you're that far away. It's a little bit dramatized at times, but it's really, really good. It has that kind of The Martian vibe to me, which we can thank Andy Weir for, and I highly recommend it. I'll see if I can think of an educational resource when it comes to astronomy. Is there a nice book I read recently? Not really. I don't read that many books, especially on astronomy, because I read papers, but they'll be boring.
So I would also like to tell my readers about your website. You can check the Helosi's website, and it has many beautiful illustrations and many beautiful
Oh,
diagrams
thank you
which you
so
can look.
much.
Yeah, actually they are pretty nice. I have looked at them, and actually they're quite nice, and you should look about them. So, hello, Sid. Thank you for having us with today and this beautiful talk session about astronomy, where you took us through from the history of astronomy, starting from Big Bang, 1600, about various scientists, how astrology and astronomy are related, and everything, and how you told also about nuclear pasta. I should come on that
Thank
now.
you so much, Amik, for inviting me. This was so much fun.
This is our pleasure. Thank you, Eloise.